So, thank you for being here. We're going to discuss the Omnitrace. It's one of the tools about profiling. I will not mention again all of this because that was already mentioned. So it will be Omnitrace will be here. And basically, if we can say with one word, the difference is that here you can see the timeline, what happens during the execution of an application and the various events that you use. And you can see much more information than what you could do with RockProf. While the next tool is focused on the kernels. So the next tools doesn't care about MPI, communication, etc. It's only about kernel performance. While here is more about all the timeline, NMPI, etc. Doesn't do an analysis of MPI, more event records, etc. So Bob mentioned already this stuff, so I will not talk again because this talk is about to be separate. RockProf is a product from AMD. Omnitrace, Omniprof is are the research tools from AMD, which means they are not official products, but they are research tools, open source. For example, Omnitrace is here. You can find to install, documentation, etc. Is not part of RockM stack, which means you have to install it yourself or the support team of the supercomputer, etc. It's not by default. It supports many languages, C++, Fortran, Python, OpenCL, various data collection modes, dynamic segmentation, statistical process sampling, causal profiling. Data analysis is with various options, high-level summary, comprehensive trace, critical trace analysis. And parallelism, MPI, OpenMP, pthreads, heap, HSA, Cocos. Here, as mentioned here, that OpenMP is mainly for CPU, I would say. The counters, hardware counters, HSA API, heap API, heap trace, HSA trace, and memory and thermals through RockM SMI and other stuff. And CPU counters, also hardware counters, like the PAPI, timing metrics, memory access, network, I/O, and more. Just to mention something, it provides extra information, CPU plus GPU, on the same timeline to see more information. Now, installation of these tools are extremely easy. You don't need root access. This is an example that I want the latest Omnitrace version. I have RockM version 5.43. Of course, here you declare whatever you have. Then export Omnitrace install directory where you want to install it, somewhere that you have permission to write. And then wget, the wget includes the Omnitrace version that you include here. And then you install it on the path that you want and for the RockM that you have declared. So all the dependencies are built automatically. And you can set up the environment like source this one or use a module stuff that exists. It's extremely easy and the full documentation is here, not for installation, for using the tool also, etc. Now, the Omnitrace, the instrumentation modes. There is a dynamic binary instrumentation, characterize performance, sample every invocation, large overhead. By dynamic, it will go to every dependency of the binary and the modules and everything. And the overhead can be extreme. We'll see some examples. I really kind of avoid this type of instrumentation because of the overhead. Because imagine if you have a huge overhead, you don't know what to trust. You don't know what the results to trust, okay? Sampling, a periodic sampling of entire application, statistical sampling or process sampling. This is like I want to sample every few microseconds or whatever you want, my application. I'm also not extremely fan of this mode, but if you have an application running, I don't know, for 12 hours, 16 hours, maybe sampling is better than normal because sampling will create less data, less overhead and less data, okay? And you'll be able to analyze data. If you do tracing for 12 hours execution of application, you will have a lot of data. So it depends what you want to extract from your application and how long it runs and all of this information. Now, basic command line syntax. After you have loaded the module, it's Omnitrace, options for Omnitrace, dash, then is your command and arguments. Your command is usually your binary, and if you have any arguments for the binary. So after the dash is your stuff, your binary, and before is Omnitrace, and of course the srun, like here is srun, options, Omnitrace options, dash cmd, the binary and the arguments, okay? With Omnitrace -h, you can see the help. There's a lot of stuff to see about various options that what you can do. And of course, you can create an issue here. When you have an issue with this tool, you can totally create an issue here and developers will see it and they will try to accommodate your request. And there's the documentation available here. So we're quite open source, and this is open source access to issues. Also, you can see other issues before you create an issue, search, and maybe it's already declared and they will be working on it, etc. Now, let me explain something. In order to Omnitrace to work, it needs a configuration file. Why? It needs to understand what you want to do with Omnitrace. By default, it has some activated options, but you are not for sure if this is what you want. So in order to see the categories of various options that you have, you can execute Omnitrace avail categories and again options. To see information about what's the options here for the avail, you can do Omnitrace avail -h again. And I'll collect information for categories for Perfetto. I can do -c Perfetto, for example. And then you can see with this command, for example, you can see the options for Perfetto environment variables, their value, and which categories they belong to. Now, the configuration file basically has environment variables and their values, okay? And I will show you the way to see what are the options and how to create, of course, one. Now, if you do -c Omnitrace, it will show you the category Omnitrace. But what's more important, if you do -bd, is brief description. So now you see the various Omnitrace variables, environment variables, and a description that you can read to understand what is this variable. So there's a lot of information about the variables and without you wondering, oh, what to do now or what to change. Now, how to create our own file, right? We'll do Omnitrace avail, -c. It can be in our home or in another place, doesn't matter. And I call it omnitrace.cfg. Now, this one command will create an omnitrace.cfg file with a list of environment variables and their values. If you want for each variable, it's like basically it's like this one, it's like here. If you want for each variable to have a description of what is this variable, you add -all, and a few lines description will be before the variable for each variable. This way, when you go to your file, you will remember, okay, what this variable does. And then, when you create this file, you have to declare it as Omnitrace config file, path to omnitrace.cfg. Okay, so we'll create a file that needs to be used from Omnitrace, but Omnitrace, in order to read it, it needs to be declared. If you don't declare it, Omnitrace doesn't know that this file exists even. Okay, so it will run with some default options, but not what you want. Now, let's see the dynamic instrumentation. Although in the HackMD, I think I have a path from where to copy these HPC training examples. Okay, no need to clone it again, I think, because we have changed the Jacobi make file also. Then we do CD HPC training examples, heap Jacobi. We compile Jacobi and we run it. Now I run it without anything, just the binary. It takes 2.1 seconds. If I say, and of course this is SRAN, okay? If I say SRAN, Omnitrace instrument, this is dynamic instrumentation, does Jacobi heap and the options, it took 1 minute 45 seconds. From 2 seconds, it went to 105. This is like 50 times overhead. That was extreme and a lot. And this is coming from Dynast reading every binary that's loaded, not overhead of Omnitrace during app execution, but it is because of the dynamic instrumentation. And here we can see while we compile and while executing the all of the stuff, we can see the functions instrumented and passing of the libraries, etc. As also, and we can here see, and we can do a trick. What is that? We can execute Omnitrace instrument, does v1, simulate. This means it don't run this command, but simulate it. Print available functions, does Jacobi. Now, here the does v, okay, is a verbose output of the Omnitrace. The simulate flags does not run the executable, but only demonstrates the available functions. And then it starts printing all the available functions from everywhere. And this can be a significant list. So here you can see that you access really a lot of functions and other modules and libraries, and this takes a lot of time and overhead for the application. Now, if you want, for example, to include, you can do the following. Does I Jacobi, for example, this and Jacobi iteration. This means that profile only these two iterations. And you can see it here that only these two functions are shown to be instrumented when you do here. Okay, so with does I, you can include which routine you want to instrument. Does E is for exclude. Okay, so till now the dynamic instrumentation provides an approach, but it's with quite a lot of overhead. So something we can do is binary rewriting. And what do we mean by that? I can say Omnitrace instrument any options, does O new binary, does the executable. This will generate a new executable library with instrumentation built in. Okay, so for example, instrument does Jacobi heap.inst does Jacobi heap. Okay, so this way we create an instrumented binary which will profile only the functions that are around the code of this basically binary, and not all the modules and the libraries and etc. stuff that dynamic instrumentation does. Now, default instrumentation is main function and functions of 1000 instructions and more for CPU. So if a CPU function is less than 1000 instructions, maybe you will not see it in the trace. To instrument routines for 50 or more cycles, you can add the options does I50, but this will cause more overhead. So you need to have a specific reason to do that. Otherwise, it doesn't really make sense. And of course, when you run this, you can see that how many modules it processed, it found the PI need, and it creates some files. This files is basically more about not when you run, but when you create the binary. Okay, when you do this command to create the binary, and you see the path to the new instrumented binary, right? .inst we call it. Now, I have the binary. How I run it? srun dash n1, omnitrace run. Now omnitrace dash run dash Jacobi heap inst is the new one, the instrumented Jacobi, and the options. So in order to run it, is omnitrace run dash and the new binary. It's quite simple. Binary rewriting is recommended for runs with multiple ranks. If you run API or something with multiple ranks, do binary rewriting. Don't do dynamic instrumentation because it can create problems and there is a big possibility to fail to run also. So, and now it runs, and actually now it's around 1.5 seconds, right? It says here, maybe the time is not included here basically, but it's a bit around over 2 seconds. So from, sorry, I have to go back from 1 minute, from 1 minute 45 seconds, it's a bit above 2 seconds now. So you can see that the binary rewriting helps a lot to solve these issues with the overhead. Now, let me go back again. It's not here, but when you run something, it will create directory omnitrace binary dash output timestamp. This way you have all your experiments in different subdirectories. And if I load the file rocktracer 0txt, I can see the rockmtracer activity. Over here you can see a list of kernels, etc. You can see Jacobi iteration on kernel and other stuff. Now you can be a bit surprised to see it multiple times some stuff. There's a units, okay, seconds, some mean values, percentage of self, but the percentage of the self is not really good here. And how many counts it was called. So you see here, for example, the computation kernel here is called 40 times, but here is the main execution, for example, 990 times, etc. And there's like, as you see, there is like a call stack here, okay? That the heap last kernel will call the Jacobi iteration kernel and normal kernel 1. Now, the rock tracer is, the txt is created if you have activated the rock tracer in the configuration file of Omnitrace. If it's not configured, it will not create it. Also, it creates a perfetto file. So I copy the perfetto file, I go to this web page, I say click open trace file, and I select the perfetto file. The file is like that. What you see directly is that you can see some information like the main, API need, some Jacobi stuff, and you have to zoom more to see the numbers. But you can see a lot of CPU frequency. This one is captured statistically, and I don't think that's like 100% accurate because it's statistics. And there's a lot here. You can see like I think 128 because with the threads together CPU frequency. So this can be a little too much things to watch. But we can remove this, and I think I will show you later how to remove these lines if you don't need them. And of course, here is the XY is the time, and you can see here how big is the call stack. Yeah, trace of CPU, functions, CPU metrics. So here's a zoom in, and you start seeing how it's called events, right? Heap large kernel running a kernel, API exchange, hello world all, various things. So you can see heap memory copy, etc. So you can see all of the events while you zoom. And basically how you zoom, yes, is the W to zoom, S to zoom out, A to zoom left, and D to zoom right. Now, zooming in to investigate regions of interest. So the flow events, when you click the heap launch kernel, it draws you with an arrow, okay, which kernel activated and run. So it's kind of easy to track. Select values of interest to view close together. It's from here. It depends again on what kernel you have. And this is GPU characteristics. GPU busy is the time of the percentage when it's busy the GPU, right? Doesn't mean efficient or not efficient workload, but it means there is workload. And also CPU memory usage, the GPU temperature. These ones are captured from ROC MSMI, so it's statistically running I don't know exactly when, every few microseconds, and it's not 100% accurate. And we'll talk about some counters that you can take some information. Okay, so now about hardware counters. If you do srun n1 Omnitrace avail all, you'll start seeing everything. Now, although this is better to do it when you have a reserved one GPU, so all the GPU environment is activated, loaded. And you can see the components categories that I never really use this one. Environment variables and their values and some explanation. For CPU, hardware counters, now this is a public hardware counters, and the performance structured again. This one can be from the CPU, all of them are from CPU. You have GPU counters, okay, and explain it here what is that, it's counter. Now, the device 0 means this is for device 0. If you run like 8 GPUs, this will use the counters only from the GPU 0. If you remove this, then it will be used for all the available GPUs. Now, Bob already said to you about the commonly used GPU counters. It's the same, so I don't think there's reason to repeat it. And how you add hardware counters to your config file. You remember you created the config file here, right? To add the design metrics, you define Omnitrace ROCm events, and you say, for example, GPU busy device equals 0, wavefronts device equals 0. This means I will use only the hardware counters for device 0. In order to use hardware counters for all the GPUs, you need to remove the device equals 0 and call like that. This way, you will profile the hardware counters from all the GPUs. Now, when executed with hardware counters, like the Jacobi, right, then you will see the output of getting the Jacobi heap output, and here the timestamp, you see GPU busy, wavefronts, memory unit busy, etc. This means that your counters were correctly declared and you create data. If you run it and you don't see any counters while you use counters, probably there is a mistake, typo or something, and it didn't really take under consideration the counters. So you have to be careful in that situation. And now, what we visualize with hardware counters, again, you will click somewhere and you see, but now you see the following. Device CPU busy, GPU busy. So the hardware counters are more accurate, are not the statistics, and if device means exactly that. It's coming from device and not from statistics sampling. And so that's why you see also here the S, right? While here there is no S. So it was impressive to see that when you use a hardware counters, you can see some differences many of times compared to sampling. Yeah, here's the CPU activity and the GPU activity down. Yeah, this example also have RockTX regions that basically this is the markers that can also visualize and show them. Tracing multiple ranks. So before you saw in the RockProf, you had to do some tricks, right? Some scripting, etc., etc., etc. Here, there is no such problem. You instrument the binary. You basically you rewrite the binary. As we said for MPI, you need to rewrite the binary. You execute it, and that's it. You will take one file per MPI process. Okay, so it's quite straightforward, I would say. I don't know, is there a question till here?
Nothing in the chat.
Okay, so you take one file per MPI process, and of course one perfecto per MPI process, and then here you can visualize and see MPI process 0, MPI process 1. That's nice because you can see different API processes. Now, of course, the question is, if I have 200, no, I would say that's complicated even to analyze them yourself by checking with your eyes. This is an example for small API processes. I would say for bigger ones, you need to probably do some scripting, etc., to read the file and understand what you want to check. However, the Perfetto has a nice file format that you can do, for example, merge them like that. Cut the Perfetto the 0 and 1 to all processes, and then visualize, and you see the two MPI processes together in the same Perfetto. That's really easy to mix and easy to see differences, right? You can see, oh, this one took much lesser time than the other one, for example. And you can investigate if there was a problem, or it happened once, or you can reproduce it, etc., etc. Now, statistical sampling. The original, when you use Omnitrace, you will take something like that. Okay. When you do Omnitrace, you use sampling through, in your CFG file, in your configuration file, you have a many environment variables. When you declare here to use sampling, and the sampling frequency is 100, which means 100 samples per second, you can do even more, then you can take all the call stack, and you can see how deep it goes, all the call stack. And this is important many times to understand from where is coming this code, for example, right? Or from which call stack really call this code. That's quite important. And now if I zoom in, you can start seeing that from here, call this, and then this, and it continues like that. When you click one, that same color, or the same color, then it will be highlighted. So you know where are you and what to track. This is really nice and something that the Perfetto doesn't, the RockProf doesn't do it. And it's really interesting to understand where are you in the code, etc., from where is it is called, and for any other issues. Now, other features, kernel durations. If you check the work log, okay, is the durations. Now, if you don't see a work log txt dumped by Omnitrace, modify the config file and enable Omnitrace time memory, use time memory, T memory. It's true. This one, I will activate and you see the wall clock like that. Okay? With the order of the events that are called in some iterations, you can see the event, you can see how many times it's called, etc. in the call stack. And also, text files for quick reference, JSON output is easy to script for and can be run by Python packets. Now, flat profile. Flat profile is quite important. In your CFG file, you do memory true and flat profile true. And then you can see for each, let's say, routine, kernel, etc., how much time it took. You'll be presented only once for all the applications and nothing else. So you can see how many times, path, metric, units, some of the time, and min of the time. And this is quite important because with a flat profile, you can, with the help of a script, you can sort and extract, for example, the 10 most time-consuming functions, kernels, whatever you need. That's why the flat profile is quite good to investigate every time you run something. Now, the user API, basically, you can use user API to start tracing, stop tracing, start thread trace, stop thread trace, start user-defined region, and user-defined region. And this way is because if you have a big code that you submit everything and you have a lot of garbages, a lot of other stuff that you don't care, or it takes much more time, you can select to start and finish the compiler specific part of the code, which can be short or can be the most part that you want, and also can be smaller than the trace files, and at the time also to analyze it. So this can be useful in some cases, just to be aware. And all the API calls are here. Now, OpenAP. We use an example. It's an Omnitrace examples OpenAP. Doesn't matter, build the code, I define 4 OpenAP threads, and I run the OpenAP LU. And how instrumented? OpenAP instrument does O, the instrument binary, does this. So this one will create a new binary and we'll run it with this option. With 4 OpenAP threads, Omnitrace run that does OpenAP lu.inst. Okay, because as we said, when it's many processes we do binary writing, we don't try to do dynamic segmentation, and we just make a new binary and we run it. And when you run it and you see the wall clock, this is the wall clock timer, you will see now 4 processes, okay, 1, 2, 3, 4, and how many times is counted, the metric, the time, the sum, etc. And so this way you can see per OpenAP process what's going on. And of course also you can visualize that. And if you visualize, you will see now again on the perfetto 1, 2, 3, 4, and you will see some various calls from each thread. Okay, so to take an idea what's going on, and I hope later to be even better. Now, what about Python? The Python documentation is here. Okay, and when you install Python, to set up the environment, you can do Python path equal to this one, and Python path again. We use Fibonacci example in which denominates examples Python source PI, and execute the Python program, Omnitrace Python and the program. So this one will create a directory Omnitrace-source -output, and with a lot of data here, depends on what this Python does. And here you can see in our CLI, you can see what this is Fibonacci, and you can see how many times it's called, the time, okay, minimum, min, max, variation state v, and of course how many times it's called this function. And you can see how easily we can visualize, see the Python. Of course, to visualize Python, we can visualize it again easily like that. And you see the Fibonacci. There are many functions yet. But here you can see how the structure of Fibonacci value visualize, okay? It's quite easy to understand and see if something goes wrong also. Cocos. Now I was in a hackathon and they told me we have Cocos and we like to profile it. I said I haven't done profiling with Cocos. I went to the configuration file. I activated the Cocos, just ran it, and we were able to get data about the memory of Cocos and have check how much memory I will consume depending on what we call, okay? So it was really nice to see that this works without really doing something critical, just enabling a Cocos variable. Again, visualizing, you can see here how we go more and more inside. You can see visualize Cocos. It's like the call stack, etc. You can see all the information. And something new, causal profiling. For this one, I don't have exercises now because it's something really new, but I wanted to tell you what it is. Many people have seen it first time, even this wording. Now, causal profiling is something that demands multiple experiments. Each experiment has two independent variables. Let's say the function that you want to investigate or the line of code selected for the experiment, and the virtual speed amount. I will explain in the next slide what's virtual speed amount. It requires multiple runs of the application. For each function, the baseline of generation is 0% virtual speed up compared to the other functions. And it requires 1 plus virtual speed up over 0% to make investigations about the other routines. Speed up prediction is highly dependent on a baseline. Process points are required, exception end-to-end run. Process points are the points that when we run from there, the tool does investigation, what happened with the data. Supports sample space of fixed speedups, binary scope pattern, function scope pattern, source scope pattern, line scope pattern. For now, it's only for CPU threads and workload, work in progress for GPU kernels. There's a GUI available, but I think maybe it's not ready yet. We use the example from the Omnitrace, which is located here. And you can see the documentation from here. Now, if I have to explain something, let's see on x-axis, this is time, okay? Time is here. This is time. We go straight, this time. And, sorry, time is like that. And you have two threads. And they call function 1, function 2, function 3, function 4, function 5. And you can say that this is also MPI processes and they call the same functions, etc. I mean, for now, we say that this is threads and they call some different workload, okay? And I would like to know if I improve function 4, do I get any improvement in the performance of the application or not? This is CPU only, right? And so the question is, how to know if I improve the application, if I can take some significant impact on the total application? So there's one idea. In order to increase the performance of this, what means increase? It means decrease the execution time. Instead of decrease execution time, what if I delay the execution of this? Meaning, from what it is here, what if I do this? Well, this is an overhead, but this is the percentage of what I improved here it's I push this like that. So this takes more time, and this can finish later. We don't know yet. But if I push this a bit, the duration of expected optimization here, then I will be able to compare and analyze what happens with the values, with the quite significant scripts and other things. So the philosophy of this is instead of to optimize something which I cannot optimize before I fix a code, what if I delay the other thread? So to run faster and to understand what's the benefit. This is the main concept here. So how it starts, I would say. Generate a flat profile. You can remember the flat profile is about take the top 10 kernels that take most of the time. Get familiar with the functions that take most of the time. Is set throughput progress points in high traffic area. Progress point is a generic term. It's basically something that it can be MPI call, Cocos call, OpenMP call, something different, and it can be also the user API that I think it's in the next or a bit later slide. Now, reduce the virtual speedup sampling case default 0 to 100 in increments of 5. So you can define speedups depending on what you want, but from 0 and later. With these speedups is a virtual speedup how much to delay the other routine to achieve my target. Use scoping to restrict the experiment sampling space. I will show you what is that. A binary scope, source scope, function scope, line scope, etc. And use the function mode initially because it reduces the experiment sampling space, and use the line mode in combination with a strict function space, function scope. So let's see something. Basically, this slide should be later. Source scope is to restrict to lines 100 to 110. In the options I will show you in the next slide, you can add, I want to do analysis per line, and I want to analyze lines 100 to 110. So this way, all the analysis will take place here. Or function scope excludes functions which start with Cocos or std enable if. And this one will exclude the functions that start with Cocos or the std enable if. This is about to exclude some functions that we don't want to analyze because it will take more time, more overhead, etc. Now, I use an example. Causal CPU Omni is provided by Omnitrace, and it has basically it's a C++ code that has two functions which are really toy case. One is fast and one is slow. I would do it on purpose to be slow. You can take fraction, how much slower to do it, etc. So, for example, when I run it here for 2 threads, okay, it says fraction of faster to slow is 70%, how many iterations, other stuff. And you can see that my slow function is, this is 10,000 microsecond, and the fast is 7,000. This is 70%, right? It's 7,000. The total execution is this one, ratio, and RDIF is this one. The source code for this example is here. Okay, so I will not show you the source code because it's basically C++ code, and they define some of the progress points, and I will tell you later how you define the progress points also. And this is a script that to run various cases that I would like to explain a bit. Here, this script creates a configuration file for itself. Okay, I have to define the output prefix, output path, okay, and it's the causal backend used. This is to show that this is the causal backend is activated. and I define where's my Omnitrace config file. Then what I'm doing, speed ups. How much speed up do I want for my code to compare with the other threads? 0. 0 means nothing. 20 to 40 by 5, it means 20, 25, 30, 35, 40. 50, 60 to 90, 70. So this way I define various speedups. Okay, and then that's no reason for here. Then here I call the Omnitrace causal. There is no reset. The reset is empty. Execute 5 times the code for these speedups for functions, and does and the binary. This will do the functions, okay, that define the code. However, some functions are not interesting because they're from other files. And I do function, but please scope only this file, which this file is my code. No need to check for other files or other routines that I have no access, etc. And the output of the file is experiment.func. And again, I call causal CPU omni. Okay, and now I know that I have 2 specific routines, right? So I can say, please scope for source code line, same file, but now include the functions CPU slow func and CPU fast func. So now I give the name of the functions and for the line analysis, and I call it experiment.line the output. Again, does and execute it. Okay, and the last one is does here means I have no progress point. That means I haven't defined any specific point that I want to verify. So again, scoping the causal.cpp and the functions slow and fast, output line .e to do e. This is up to you, it doesn't matter. And does C means it goes from the start to the end. I have no specific progress point inside. And then after this all finishes, the create JSON file that I can visualize. Progress points could be MPI, Cocos, Rock Tracer, and other calls. You can use user API to declare in your code the progress points. So how you do that? Include Omnitrace causal.h, define causal progress. You can define this macro. Okay, that this calls basically Omnitrace causal progress. Causal progress named, Omnitrace causal progress named, causal beginning, causal end. Okay, label, and how you can make it call it, for example. This way you can begin, end some causal stuff, and etc. You can control it so not to be really huge also. And this is what happens. What you see here is 1, 2, 3, 4 different groups of